All right, today we are taking a seriously mind-bending journey. We're heading to the most extreme destinations in the entire cosmos, black holes. We're going to start with a virtual plunge right into one, and believe me, we'll end up on the hunt for some truly theoretical monsters that might be lurking out there in the dark. So let's get right into it. So imagine you could get a front row ticket to the absolute edge of reality. Well, back in May of 2024, NASA dropped this groundbreaking new simulation that pretty much does just that. It's a first-person trip, your trip, across a black hole's event horizon. You know, the literal point of no return. And we're not talking about just any old black hole. Nope. The simulation takes us to a supermassive beast that weighs in at 4.3 million times the mass of our own sun. Now, just to put that in perspective for you, that's the same scale as Sagittarius A star, the monster sitting right in the middle of our own Milky Way galaxy. And look, this isn't science fiction. This isn't some Hollywood special effect. This visualization was built by a supercomputer that crunched about 10 terabytes of data. It is a scientifically accurate journey that shows you exactly how Einstein's theory of general relativity would twist and distort reality as you fall in. But, and this is a big but, to make these incredibly complex calculations even possible, the scientists had to make one key simplification. The black hole in their simulation, it's perfectly still. It isn't spinning. Now here's why that really matters. The spectacular journey, as scientifically real as it is, shows us a type of black hole that's probably incredibly rare. The reality of the cosmos is, well, it's a lot more chaotic. So what happens when we add that spin back into the equation? Well, that's where things get really weird. You see, most black holes in the universe do spin, and some of them spin unbelievably fast. When they do, they don't just warp space, they violently drag space itself along for the ride. So this kind of breaks it down. On the left, you've got this simple, non-rotating, Schwarzschild black hole from that NASA simulation. It's a perfect sphere, and you only need to know its mass to describe it. But on the right, that's the far more common Kerr black hole. Because it's spinning, it actually gets squashed at the poles a bit, and it has this truly bizarre feature called an ergosphere. Okay, try to imagine this. You're in a whirlpool so powerful that you couldn't stay in one place, even if you had the strongest rocket engine ever built. That's the ergosphere. You are physically forced to move with the black hole's rotation because space-time itself is being dragged along. You can, in theory, still escape from this region. It's outside the event horizon, but you absolutely cannot stand still. It's just a mind-boggling consequence of adding spin to the mix. So, we've gone from a simple, static black hole to a spinning one. But what if we just push the scales even further? I mean, we know about supermassive black holes, but are they really the biggest things out there? In this question, this takes us to the absolute frontier of theoretical astrophysics. While it seems like there are upper limits on how big a black hole can get through, normal galaxy stuff, some theories suggest there might be a whole other class of objects out there that just dwarfs everything we've ever seen. And here they are. Say hello to stupendously large black holes, or SLABS for short. You gotta love that name, right? We are talking about objects with masses starting at 100 billion suns and going up from there. That is an object more massive than many entire galaxies, all condensed down into a single point. So how could something this monstrous even exist? Well, there are two main ideas floating around. One is that they could be the absolute rarest, largest outliers that form in the centers of giant galaxy clusters over cosmic history, or, and this one's the wilder idea, they could be primordial, born directly from the dense, fiery, chaotic soup of the very early universe, long before a single star or galaxy ever existed. Okay, so if these cosmic monsters are really out there, how in the world would we ever find them? I mean, by definition, they don't shine. So how do you hunt for something that's both stupendously large and perfectly invisible? Well, the answer is you don't actually look for the slab itself. You have to become a cosmic detective. You look for the enormous gravitational footprints it leaves on everything around it. I mean, think about it. An object with this much mass would be impossible to hide from the laws of physics. And this right here is the detective's toolkit. First, you look for extreme gravitational lensing. A slab passing in front of a distant galaxy would warp its light in a really distinct, powerful way. Second, you search for signs of chaos in galaxy clusters, galaxies getting pulled apart or thrown around for no obvious reason. And third, you look for giant cold spots or other weird irregularities in the cosmic microwave background. The echo of the Big Bang itself. So let's just bring this all back together. We started with a simulation of a familiar-sized black hole. Then we journeyed into the pure weirdness of spin, and from there we went all the way out to the theoretical edge of what's even possible. This whole journey just goes to show how much our understanding is still evolving. What started as just a mathematical curiosity in Einstein's equations has become a totally central part of our cosmic story, from the hearts of galaxies to these theoretical behemoths that might be just wandering silently through the void. And that leads us to this final provocative thought. The search for slabs is this powerful reminder that, the universe is under absolutely no obligation to make sense to us. If these cosmic monsters really are out there, hiding just by virtue of their own darkness, it just makes you wonder, what else have we not yet even learned how to see?